Hey, Algebra. I'm going to go over the practice problems for 83 here. And we've done factoring trinomials. And these trinomials can be factored the way we learned how to. That doesn't change that. Really, today is a special lesson about looking for patterns because you're going to need to, this will make things a lot easier for you for some future lessons here. Okay, so you want to understand how this method works because it will make it easier later. If you don't learn this method, there's a lesson coming up later that's going to be a challenge for you, okay? So don't just always go to, well, I already know how to do this my way, so I'm just going to stick with that method. Understand and learn this method so that it helps you later. So we're really looking for patterns. So for these perfect square trinomials, the pattern we're looking for is this a squared plus 2 times ab plus b squared. And that means that our factored binomial will look like this. So whatever the a and the b are, squared, okay? And if it's subtraction, or if we have a negative here, then our factored binomial will be negative. Again, and this is just a pattern to memorize and recognize that you see to help not only recognize the pattern, but make the work easier for you. Okay, so remembering this, let's look at this first one. We have x squared plus 14x plus 49. And the way that you've already learned, you probably could factor this very easily. But let's look at this new method. So our a here, right, we have this one or x. So think of a as equaling, don't worry about the one, just remember it there. So our a is x, and our b is 7. And we want to see, is this a perfect square trinomial? When I multiply 7 times 7, do I get, and then again, look at the pattern here. So if I multiply the a, which is x, 2 times x times 7 is 14x. Sure enough, it's right here. So with that knowledge, I can just go, yep, this is a perfect square trinomial. So it's going to factor to a plus b squared, which in our case, a is x, b is 7 squared. Just recognizing the pattern. Let's go to b. So b, we're going to add 6n to the 4th plus, it's actually minus 12, I believe it's n squared, but I'll check again here, and then plus 6. First thing right away you should see is you can factor a 6 out of all these terms. So let's factor that 6 out. Remember, this 6 doesn't go away when we factor it out. That leaves us with n to the 4th here. That 6 out of this term leaves us with 2 n to the 2nd, and 6 from the final term leaves us with 1. Remember, it's not 0. We're factoring out 6 divided by 6, which equals 1, not 0. Okay, so now, again, we want to look for this pattern. The fact that you see similar numbers here that can be perfect squares. So, for example, 49, 7 times 7 is 49. You know that 1 times 1 is 1. Look at these two terms ago. I bet you this is a perfect square trinomial. And sure enough, so in this case, our a would equal, well, this is n to the 4th, so our a would equal n squared, right? Because n squared times n squared is n to the 4th. And our b, which is this term, equals 1. So knowing the pattern, and this is subtraction, we could just say n squared minus 1 squared. And that would be our factored trinomial. Again, this is a little different. There's not as much math involved in this method because I'm just recognizing that this a and this b are perfect squares here. Well, there's two of the same number that multiply together to equal this term. So I can just pull that out and use that to set up my factored now binomial. And always check, so make sure that you did it correctly by distributing. So we have 6n squared minus 1 times n squared minus 1. Let's FOIL that. Well, n squared times n squared is n to the 4th. N squared times negative 1 is negative n squared. Negative 1 times negative n squared, and then negative 1 times negative 1 is plus 1. All right, simplify. 6 times n to the 4th minus 2n squared plus 1, and this is looking very much like our original now. And then finish by distributing the 6 n to the 4th minus 12n squared plus 6. And sure enough, this checks. We factored, so this is our answer. I'm going to make my 2's look a little bit more like 2's here. 2 and then a 2. There we go. All right, so this is our answer right here. Make it glow a little bit. But we double checked to make sure it still looked like the original trinomial. All right, and then for C, same thing as you go through. And you might want to pause the video and see if you can do this one, and then come back and check your work. So we have 3g squared. That's if you haven't already attempted. Hopefully you've already attempted most of these. But if you got stuck, that's what these videos are for. And again, I want to factor out, as I'm analyzing this, because first of all, I need to determine it's a perfect square trinomial. And if it is, I'm going to factor it. So the first two was easy to see they were because of the perfect squares here, once I factored it here. So let's factor this 3 out. So we have 3, that leaves us with g squared plus 3g plus 1. And right here, as I analyze this, well, yeah, g times g is g squared. So a equals g. And then 1 times 1 equals b, or sorry, 1 times 1 equals 1, so b equals 1. But to check if it's a perfect square trinomial, this middle term has to be 2 times a times b to be a perfect square trinomial. Well, if I plug in these values here, 2 times g, and then 2 times 1, that gives me 2g, not 3g. So this is not a perfect square trinomial. Perfect square trinomial. I have a pen input device coming that'll make my work a lot neater here for future lessons. So it's supposed to arrive next week. Okay, so D, a radio signals tower. This is, I uploaded a video, or in the Nearpod I kind of helped out with this. This is a thinker problem for sure. So we're told a radio tower signal covers a circular area with a radius r in miles. The strength of the signal is increased and now covers an area of pi r squared plus 12 pi r plus 36 pi squared miles. And they want to know how much the radius of the coverage increased. So we have pi r squared plus 12 pi r and then plus 36 pi. All right, so first thing I can see right away, I can factor pi out of all these. So let me do that. Let's just factor this trinomial and see what's going on here first. All right, that leaves me with 12r right here plus 36. And then my brain's thinking, of course, well, since we're doing a lesson on perfect square trinomials, I want to check and make sure this is a perfect square trinomial. So my a equals, so here's the a is r squared, so a equals r. Well, not a is r squared, but this term is r squared, which is a squared. So we know that a equals r. and b is this last term. It equals 36. Well, 6 times 6 is 36. And then let's check this center term to make sure if it's a perfect square. So the center term, remember, is always 2 times a times b. And if this is a perfect square, it'll match that center term. So 2 times r times 6. Well, yep, that equals 12r. So it's safe to say this is a perfect square, so I can just shortcut. It'll be r plus 6 squared. Okay? And what I want you to think of, well, this is a radio tower. It's a circular coverage area, right? So they want to see how much it increased. Well, let's compare. We know that the area of a circle is pi r squared. So if we compare in here, well, we have our pi and we have our r being squared here, and then we also have our 6 here. So if the original circle is pi r squared, the new circle is going to have an increase of 6 miles. All right, and I'm going to tell you, this is not necessarily an easy, it takes a little bit to figure it out. And I think the first time I ever did this problem, I actually had to draw the circles and really analyze what was going on there. And then I could see in the equation where that increase was happening. But ultimately, you're comparing to the equation of a circle and then how this new equation has changed. And it's changed by 6 miles. All right, now we're going to go back over to difference of two squares. Okay, so this is a different pattern. And with this pattern, you see an a squared minus a b squared. And this is really the key one for this lesson. It's going to help you out a lot later. And that'll equal this pattern, a plus b, a minus b. Because really, the original term doesn't look like a trinomial, right? So you may not be thinking trinomial and how to factor that. And that's what's going to happen is you're going to be given terms like this. You're going to be told to factor them, and it's going to throw you off because it's not a trinomial. So 25x squared minus 4. And the reason why, so again, you'll see this question later on, and you'll be told, factor this into two binomials, and it'll throw you off because there's no center term, because what happens with these is the center term cancels out by the nature of this problem. So just think, okay, well, this looks like one of those difference of two squares problems. So I'm going to see here, let me see if I can split up each term into, I have a 5 times 5 is 25. And if I can do this, and then x times x, if I can split them up into doubles here, minus, and then 4 is 2 times 2. So as long as I have a pattern, I have two 5s, two x's, two 2's, then yes, this is a difference of two squares problem. And I'll go ahead and factor it then, just like they told us to. So my a is going to be 5x, right? Because 5x times 5x is 25x squared. And my b is going to be 2, because 2 times 2 is 4. And then we're going to put it in this format. So 5x plus 2, and then 5x minus 2. And now we factor this. Okay, so just remember, when you see these perfect squares here, that it's very likely this is a trinomial, but the center terms canceled out. So that's why it's not a trinomial, if that makes sense. I know that doesn't make sense the way I said that, but if you understand what happens is when you FOIL these, the two center terms end up canceling out, and you're left with only two terms. But it can still factor into two binomials. All right, F. We have 9b squared minus 100a squared. So let me switch colors here. So we have 9b squared minus 100. I already forgot a squared. Okay. So again, just looking and going, okay, I got a 9, 100. This looks like it's potentially a difference of two squares. Let's see if we can split it up. Well, 3 times 3 is 9. Yep. There's 2 that are the same. And then b times b is b squared. Yep, there's 2 that are the same there as well. And then 10 times 10 is 100. And a times a is a squared. So see how we can split it all up into these pairs. So yes, this is going to be a difference of two squares. Let's start doing the math then. So that means that my a term is going to equal 3b. I'm just looking at here, the 3 and the b, because 3b times 3b is 9b squared, which is up here. And then our b term, our last term here in the pattern, is going to be 10a, because 10a times 10a is 100a. And then I could just fill it in. So 3, remember I'm going off of this original equation up here still, now that I've identified that it is a difference of two squares. And then plus 10a and 3b minus 10a. All right, and then of course on any assessment or anything, you always want to double check and make sure that this foils back into the original. And you can see here with that plus and minus that those center terms, they're gonna, when you add them together, it's going to, that term's going to zero out. Okay, G, we have x squared minus 14. So x squared minus 14. Looking for those perfect squares, well, I have x times x, it works over here, but does any number times itself equal 14? No. So 7 plus 7 equals 14, but not 7 times 7. So there's no number that equals this, so this is not a difference of squares. Oh, trying to do this fast. It's hard to, as you, any of you guys working with Cami, you know this is not that easy. It gets better as you get used to it. Not a difference of two squares. All right, and then for the final problem, we have another word problem. This is a long lesson. It probably should have been really 2 lessons, but I do like that they had the two, that you're comparing the two different patterns. So a square border is designed around a square pool. Use the difference of two squares to write and factor an expression that represents the area of the border. Okay, so let me break this down. We just need an expression. We need to represent the area of this border. I know area is, so it's going to be 34. So it'll be this side, actually 34 squared, and then minus s squared. And they want us to go ahead and use an expression that represents the area of this border. So, and I just got this from saying, well, 34 times 34 will be the large square, and then s times s will be the smaller square. So if I take the largest square and subtract the smaller square from it, I'm going to get the area. So 34 squared minus s squared. And they're wanting us to do this. Okay. So sure enough, this follows the pattern. And a minus b. So a squared minus b squared. And if you notice, these are already out of their square form for us. So it might throw you off a little bit that the s here is in the second term. But for the purpose of what we're doing right now, that's perfectly legitimate. So a equals 34, right? Because we're just squaring 34, and b equals s. So let's put it in that equation. So we have 34 plus s, and then 34 minus s. And we were able to answer the problem, use the difference of two squares to write and factor. That's the second part is where I factored it, expression that represents the area of the border. All right, hope this helps a little bit. Not denying that this isn't a little bit of a brain stretcher, okay? But really the idea is that you're using patterns to compare and pull out information so that you can factor these a little easier.